suppose I want to know if, given some vectors, whether or not they're dependent or linearly independent. Okay. The question is, how do I figure that out? Is there a procedure that exists where it will definitively tell me whether or not I can write one in terms of the other? So let's see. Let's take a moment. Suppose that we have three vectors, right? 1, 2, 3, 2, 4, 2. My question is, are these linear or taken together, all together? Can I find a linear combination of the two? To write the other third. And by the way, the choice of what you do doesn't matter, okay? Because you can move this to this side, divide both sides by alpha 1, and you get, the same equation. So the choice is arbitrary in terms of which one you've picked here. So anyway, does there exist an alpha 1, alpha 2, such that when I multiply them by these vectors, I get this? Well, actually, if you notice, there's a more compact way of writing this, which is as follows. So the question then is, can I find an alpha 1, alpha 2 so that when I plug it in here and multiply it by the matrix, I get the 4, 2? That's the goal, right? If I can do that, if there exists a solution for me to do that, then they're linearly dependent. On the other hand, if I can't do that, if there does not exist an alpha 1 and alpha 2, such that when I multiply it by the matrix, I get this, then they're linearly independent. Okay? It really is as simple as that. Or I should say the only alpha 1, alpha 2 it would be 0, 0, basically. And that would be it. Well, okay, I got to be careful with that. Not 0, 0. There just doesn't exist one. So anyway, keeping this consideration into mind, suppose that there existed an inverse to this. So that is, suppose there existed another matrix, whatever that matrix is, which I'll denote as its inverse. And I multiply that by both sides. We said that if the inverse exists, then we get the identity matrix. And remember the definition of the identity matrix. It's any matrix that, it's this matrix. And you'll see, that's not 11, that's just 1. You'll see that when I multiply this, I just get alpha 1, alpha 2. Okay, so determining whether or not they're linearly independent comes down to figuring out whether or not there's an inverse for the matrix. Now I have to be careful here because technically speaking, if there is not an inverse, you still can have possibly a solution here. An inverse only makes sense when you have square matrices like what we have here, versus in the event where we have non-square matrices. But all's not lost, because this motivates us to get us to a definition, which is that if we can somehow convert this matrix to an identity matrix or something that looks like an identity matrix, then we know that we can write, we've solved for the alphas, and we can write the one vector in terms of the other vectors. On the other hand, if we can't do that, then we can't write the one in terms of the other, and the vectors are linearly independent. So how do we convert a matrix from this to what basically looks like an identity matrix? Well, we can do that by We could do that by engaging in a series of what we call matrix operations. And there's three fundamental matrix operations, and they're derived from just basic algebra. Notice, if I notice these equations, right? This actually breaks down into two linear equations. This says that 4 is equal to alpha 1 times 1 plus 3 times alpha 2. This says that 2 is equal to 2 times alpha 1 plus 2 times alpha 2. Just from basic algebra, you know that whatever you do on the left-hand side here, you can also do on the right-hand side. So if I divide the left-hand side by 2, I have to divide the right-hand side by 2. But notice that this is the same as a matrix, right? So if I craft a matrix of the following, 1, 3, 4, and I put a line here to indicate equality, 2, 2, 2, I get a matrix, right? But notice, if I operate, meaning I divide both sides here, then I can basically do the same to the matrix. So if I divide both sides by 2, that's equivalent to saying divide the whole row by 2. So when I have a matrix, I can manipulate the matrix so that it doesn't alter the solutions to alpha 1 and alpha 2. In other words, this is an equivalent system to writing 4 equals alpha 1 plus 3 alpha 2. 1 is equal to alpha 1 plus alpha 2. Or put differently, this is equivalent to writing the following. They're the same matrix in the sense that it did not alter the solutions to alpha 1 and alpha 2. So there's one operation that we can do, which is that we can multiply or divide both sides or one row of a matrix by a number. And by doing that, it's not going to change anything about our solutions that the matrix is representing. So given a matrix, one operation, we call these elementary row operations, one operation is that we can just change the whole row by simply multiplying or dividing it by a number. There's a second operation, however, because here's what we can do. We can, if you remember from basic algebra, we can add these two equations together. So for example, notice I can multiply both sides by minus, right? And then I can add the two together. This is the same as 4 minus 1 on the left-hand side. And on the right-hand side, this is the same as alpha 1 alpha minus alpha 1, which goes away. And that's the same as 3 alpha 2 minus alpha 1. So what we're able to do with our basic linear equations here is multiply multiples of the row here, or of the equation, and add it to another row. So, or another equation. So the mere fact that I can multiply both sides of an equation by a number and then add it so that it changes the equation and I get a new equation, that motivates another operation we can do row-wise, which is to take multiples of rows and add them. And doing that also will not change the solution to the system here. And there's a third operation, which is that I could have wrote this. I could have put this whole equation first instead of the other way. And I got the same solution. It doesn't matter the order that I listed my equations. This motivates a third operation that we can do on matrices, which is that we can move rows around. So we have 3 elementary row operations. Multiples. If our I'm gonna shorten this up with math instead of words here. Let Ri be a row. It's a vector, okay? Be a row in a matrix. There's three things that I can do to the matrix and not change the solutions. The first thing is, as we mentioned, we can take any number and basically replace Ri with K times Ri. So for any row, I can just multiply the whole row by a number, and that's okay. The second thing that we can do, as we mentioned, is if I have another row, let's say Rj, I can take a scalar multiple and convert the Rj into Rj plus the scalar multiple of another row. That is, I can take one row in the matrix, multiply the whole thing by a number, and add it to another row, and basically change the row to the new row. And the third thing I can do is I can switch any two rows Ri and Rj with each other. So Ri now becomes Rj, and Rj now becomes Ri. Using these three elementary row operations, I can convert any matrix A into something that looks like an identity matrix. Now, why might I want to do that? I may want to do that because if it's not changing the solutions to the underlying question at hand, then what I did is convert them to vectors that are clearly linearly independent. And if it turns out that I get two vectors that look the same here, then they're not linearly independent. In other words, if I can very clearly, if I were to have these vectors, let's say, you know, these collection of vectors are not linearly independent. The reasoning is simple. I have two vectors that are the same in here. I can write one as the other. Set the number 0 to all the constants for all the other vectors. Set the number 1 here, and this is equal to 1 times that. So if I reduce the matrix down through these operations to something that looks like this, and I have more than one of them look like that, I have a dependent linear dependence. So those are the basics of matrix operations. Now I'm going to illustrate these in the following video.